All right, welcome everybody to yet another session of Laws of Natures. Today we have Tim Maudlin. Session will be moderated by Paula, and I have nothing more to do than hand over to Paula to start the session.
Okay, thank you, Dirk. So welcome everybody from my side. I'm happy that today's speaker is Tim Maudlin. He's here from the NYU. He also works at the JBI, the John Bell Institute for the Foundations of Physics, and he's very well known for several things. He's working on mostly in the field of philosophy of physics. And today's talk will be about the methodology, explicitly about the methodology of actual up-to-date physics, and I'm very excited about this. So, Tim, please go on with your talk.
Okay, thanks. Good. I mean, let me actually start out by saying the actual there is not up to date. Not up to date. In fact, the point of the actual is just the opposite. It's to think about how physics as an actual discipline has managed to function since the beginning, and it that I think has been lost a little bit in some technical machinery and hasn't been thought through how the technical mathematical machinery can be understood to make contact with the actual world. So that's really what the topic is going to be. The other thing I should say is I understand the usual way of proceeding is to start with a kind of non-technical introduction to welcome everybody in the audience, and then to get on to a sort of more normal paper that you would have in a series like this. But there's no this is an entirely non-technical paper from beginning to end, so there's no reason to do that. There's nothing here that anybody can't follow. And really, it's very much an invitation just to reflect on how physics has managed to exist as an empirical discipline, which, you might say, but wait, what's the problem? And as you'll see in a second, the problem is that there's a kind of idealized picture of how physics works that I think worms its way into people's subconscious, and then they key off that. But if you just don't do anything fancy, but just bring it to light and kind of put it in front of your face, you'd say, no, 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 physics doesn't work like that. It can't for various reasons. And then you gets you to the question, well, how in the world does it actually work? So let me just go through this. So this idealized picture, which concerns how one uses a physical theory to make empirical predictions, right? So without that, we don't have an empirical science at all. How is it that when you've got a theory in your hands, as it were, from wherever it came from, does it manage to, or can you use it to predict things you'll actually observe? And there's a kind of idealized picture of this, which is even rhetorically stated in the language of prediction. Although when you think it through, it's nothing like empirical prediction. So let's just set up the large problem is that, of course, what you're after, well, I say of course, but all of this is up for grabs. From my point of view, what you're after in physics is a clearly articulated theory, which means that you've got a very reasonably articulated ontology of whatever it is that the theory is postulating to exist at a fundamental level, and then a dynamics stated for that fundamental ontology. So, in a slogan, a physical theory should tell you what there is and what it does. Of course, and maybe I can, just say this and get out of the way. If there's anybody in the audience who's an instrumentalist who sort of thinks, wait, that's not what I want from physical theory. I just want to make predictions. I don't care how, right? I don't care if you give me an ontology. I mean, this attitude certainly floats around, and some people explicitly embrace it. Then we're just on an entirely different page. Okay, then we can have a discussion afterwards, I guess. Although there's not exactly that much to say, except from my point of view, I don't actually care much about predictions per se. All right, I'm not in the business of studying this stuff because I want to predict. I'm in the business of studying this stuff because I want to understand. And as far as I can tell, understanding involves the sorts of things I was talking about, specifying in a reasonably precise way what exists and how it behaves. And the predictions are important just from the point of view of providing evidence that the theory is correct, but the predictions aren't the point. Okay, anyway, on the part of giving the fundamental dynamics, again, we should be open. It could be a deterministic dynamics, it could be a stochastic dynamics. Classical physics, of course, was entirely deterministic at the fundamental level. Now, this kind of idealized picture is one usually associates with what's called Laplace's demon. In fact, Laplace was plagiarizing, and if you read the passage from Laplace next to the following passage by Ruđer Bošković, which was written 50 years earlier, it's clear that Laplace had read Bošković and was just more or less copying. Actually, Bošković gets the math of it a bit better than Laplace does. Anyway, so this will sound familiar, probably more familiar in the Laplace version. And so what Bošković, and again, his purpose here is really to articulate the meaning and consequences of saying you have that the fundamental laws are deterministic. And so here's the way he put it. Let me see. I was going to read. Let me see if I can. The little pictures are getting in the way. So if I don't somehow get rid of that, I'm not going to be able to read this. Let's see. There we go. Okay, so now, if the laws and forces were known, and the position, velocity, and direction of all points at any given instant, it would be possible for a mind of this type to foresee all the necessary subsequent motions and states and to predict all the phenomena that necessarily followed from them. Sorry, this is, okay, yeah. It would be possible from a single arc described by any point in an interval of continuous time, no matter how small, which was sufficient for a mind to grasp, to determine the whole of the remainder of such a continuous curve continued to infinity on either side. All right, so I hope everybody kind of gets the idea that Bošković is telling you something about how laws of forces work, and clearly no Newtonian idea in mind, that you have points, so these are point particles. He says, at a certain moment, the position, velocity, and direction of all the points, although when he's a little bit more careful at the bottom, he says, if you know any part of this arc, that's what we would say is it gives you the history of the configuration, right? If you knew how the configuration of all the particles in the universe changed over any period of time, no matter how small, so that would give you theoretically not only the positions at those times, but all of the derivatives of the positions, not just the velocity. In fact, it would give you all the derivatives. That you could then, a mind that knew that as the initial condition and knew the laws and had enough mental power could foresee, right? So here's where the predictive part comes in, right? Could foresee everything that's going to happen in the future and predict all the phenomena that followed from them. And of course, as we know, given a Newtonian dynamics, could also retrodict the entire past and as it were, work out the entire history of the universe. Um, and he says that too at the bottom because they could continue this curve to infinity on either side, right? So in a way, in such a situation, all of the information about what happens from beginning to end of time is contained in those initial conditions together with the laws, right? Um, and maybe I'll just make another side remark here. The point, Bošković's point is obviously about the idea that the laws of nature are deterministic. One can speak about that in the language of information, which is more or less what this does, right? Give me complete information about the state of the universe over any arbitrarily small period of time, and that's consistent only with one history of the universe from beginning to end. And so you can say, well, in such a case, information is preserved, right? As everybody, I guess, knows, nowadays, many more people will talk about this in terms of preservation of information. Um, I think it's just much more straightforward to talk about it as determinism because that's really what it is, especially because, as we'll see, this is not information that anybody ever has, could have, will have. Talking about it in terms of information, it seems to me, is just pointing your mind in the wrong direction, given what he's trying to express here. Anyway, this is what Bošković says, and now I can't. What's going on? Here we go. All right. So the next 6 slides are about why this passage isn't about the methodology of actual physics. Okay, so it's about what this Boškovician or Laplacian demon could in principle do. I mean, that's the rhetoric in which it's stated, but that's not the point. It's not the point is not to give you a kind of sketch of what humans can do for many reasons. And I'll go through 6 of them. And as I go through them, it might occur to you that, okay, yeah, I see what you're saying. Literally what you're saying is true, but there are ways around this, or there are ways to mitigate the problem that you're pointing out. And in some of the cases, that's true. In some of the cases, it's not true. But let's just go through why this picture of this demon making predictions can't be anything like how actual humans can use the theory to make predictions. All right. As I say, really his comment, might say, is mathematical, or insofar as it involves physics, it just says that the global dynamics is deterministic, and deterministic in the way that's appropriate for a fundamental dynamics given in terms of differential equations, right? So why can't this be the way we actually make predictions? First, well, it could turn out, and many people think it does turn out, that the dynamics, the actual dynamics of the real world might be stochastic rather than deterministic. In which case, obviously, even given the information about the present configuration of the particles and all the derivatives, and the laws, that wouldn't fix a single future and it wouldn't fix a single past. So you just couldn't make categorical predictions about what will happen, or retrodictions about what did happen. Now, again, you might say, okay, well, all right, I can adjust for that by making probabilistic predictions and retrodictions rather than categorical ones. But at least this is just ways in which this wouldn't work. Second practical observation is that even if you had all of that initial data and the fundamental dynamics were given by some differential equations and the whole thing was deterministic, we couldn't calculate it, right? We couldn't actually solve those equations, right? As you know, we get into trouble once you get beyond two bodies in Newtonian gravity. So there are all kinds of technical problems of chaos and then just everyday problems of too many variables. We kind of actually couldn't make predictions in that way. Third observation, well, we couldn't have the initial data anyway, right? There's no possible way that any human being will ever know the complete configuration on the idealization that the relevant ontology is a particle ontology, and that at any given moment there is a complete configuration of the entire universe and some number of time derivatives of it, or knowing it over some small continuous period of time to give you all the derivatives. No, nobody's ever going to know that, right? It's not possible for any actual person or group of people to be in possession of that information. There are different issues here, and lots of them will jump to your mind. There's a kind of more abstract issue which is fun to think about, which is whether any system could contain within itself a complete description of itself, right? Because it seems kind of paradoxical, because as it were, in that description, it would have to contain another description of the description, and in that, a kind of infinite hall of mirrors. So you might wonder whether it even makes sense to think that any actual system in the universe could contain within itself a representation of the entire universe and therefore a representation also of itself. And that's a sort of fun thing to think about. But then there's not enough storage. There's not enough memory. You can't, if you need absolutely precise initial data and to nail down the initial configuration with infinite precision, you can't do that. You couldn't, you could neither determine it, nor if you could determine it, could you record it, and so on. Even beyond that, there's another problem, which is that if you went about trying to figure out what the entire state of the physical universe was at any given time, some of it's going to be beyond your present horizons, at least if you think that you can't get information faster than the speed of light, then at best you have access, even in principle, only to stuff in your past light cone, whereas the kind of data that the demon has is the complete situation at some moment of time globally. So most of that is beyond the scope of your direct observation or of any inference from what you can observe, right? There are just horizons involved, at least if you take the speed of light as a kind of limit, that no subsystem could get that data, irrespective of the fact that it's too much data for it to have anyway. Fifth observation, there's just too many degrees of freedom, right, for any actual person or society or lab to observe and record all the data that you would need to do this. And at this point, the level at which these numbers outrun any practical abilities, you don't have to worry about the thing being global. You don't have to worry about there's lots of stuff you'd have to know that was outside your light cone. Um, just a single box of gas with a mole of molecules that you're sitting on your table. There's just no conceivable way, and certainly has never been the case, that any humans could have uh, e- even an approximate observation of the precise state of that gas at any time, right? Just couldn't be done, and certainly never has been done, which is really the more important point. As I said, this is about how has actual physics managed to make predictions. Now, notice in that case, and it will occur to you, yeah, but we can predict certain things about what that box of gas will do. And that's right. And the why we're able to do that and how we're able to do that, despite the fact that we can't be doing it in the demon-like way, is just the thing I want to be foregrounding here. Um, there's a sixth problem, and I don't want to spend a lot of time going into this, although it's one that I hope everyone will recognize is even more serious in a certain way than all the problems so far. And that depends on what exactly you mean by deriving empirical predictions, right? We don't just want predictions. We want empirical predictions, empirically testable predictions. Predictions of things that can't be observed would not play the methodological role that we want the predictions to play. Now you have to stop and have a conversation about what you mean by an empirical prediction or a prediction of something observable. One way that certainly this is talked about is in terms of consciousness and literal observation by a conscious being. And that in order to get an empirical prediction out of a physical theory, you need to derive literally what the conscious experiences of observers would be if that theory were true. And the obvious point here is that nobody knows, even if you could solve every other problem that I've just given you, even if you could somehow say, all right, here's this future history of the positions and velocities of all the particles in the universe from here on in. And then you ask, okay, yeah, but what would an observer see? What would their conscious experience be? Nobody knows how to derive that. That's just the mind-body problem. And nobody has a clue how to do it. So if you had to do that to make empirical predictions out of a physical theory, then it's evident that no physical theory has ever made any empirical predictions. And that's a really bad result, right? That's the result we want to avoid. Um, so again, you might, if once you make the point that this Bošković's demon or Laplace's demon picture isn't supposed to be and cannot be an account of how actual human beings make testable predictions from physical theories, I think, all of these points show that that's impossible. Okay, that's a negative result. Then the question is, but how does it work then? I mean, we do make predictions, right? We have had lots of theories and we've used them to make predictions, and some of the predictions have been awfully precise, and as it were, some of the data has been very precise, and people are always bragging about the number of decimal places. So sure, physics does work somehow. It just doesn't work this way. And it never has, and it never could. So one ought to stop and think how it actually does work. because my view is that by not focusing directly enough on this problem, have been led astray. And by the end, you'll see there are some contemporary, very lively debates going on that really center around this question, and I don't think they're being addressed the right way. All right, so that I'll leave that to the end. But as I say, these six problems, I think everyone would recognize are problems. The last one about the mind-body problem, I hope everybody. So then you say, okay, but physics does work. It just doesn't work like that. How does it work? Okay. Um, so yeah, conclusion of the first part. No theory in the history of physics has ever entailed any claims about anyone's conscious experience, right? That is, from what is postulated as the physical content of the theory, in terms of what physical items it postulates and what their dynamics are, it has never been the case and never will be the case that from that you can logically derive anything about anybody's conscious states. I just don't see how one can deny that. Good. So, question: How do we make predictions? And you might say, that it can't be the way the demon does. And remember, all the demon is doing is predicting and retrodicting the trajectories of the particles, right? All the particles in the universe. And you say, okay, yeah, but that's the kind of idealized template. It's true we don't do it that way, but we do something that approximates that, right? Or we cut some corners and put in some assumptions, and we can figure out where we do it so that what's left is something we can do as a practical matter. And but still, whether what we do is well modeled, whether this kind of very abstract demon picture is the right one to be starting with, and then you're kind of trying to cut down or implement it in some approximate way, that's the thing I want to think about, because I don't think that that's how it works. But let me go through some of the things that would occur to people, probably should occur to people, if you wanted to start with the demon and say, okay, I can't be a demon, nobody can be a demon, but still I can kind of try to be as demon-like as I can, and maybe demon-like enough to make some predictions. What can I do? All right, so one thing that will occur to you is that, yes, there would be problems about determining and making predictions from the entire state of the universe, which is the data you need to feed into the fundamental dynamics. But you might say, yeah, but I can still set up isolated subsystems. I can set up small parts of the universe in very particular physical circumstances where I can treat of them as if they were the entire universe, right? It's dealing with subsystems, and more particularly with isolated subsystems. What the isolation is supposed to do is to take out all the rest of the universe that's sitting around it as being relevant to its own development, right? So somehow you have a system where the dynamics is, as it were, effectively internal to the system, and the external influences are either eliminated, which you just do by shielding somehow, right? All right, let's put up a bunch of shielding so that stray cosmic rays can't get in. Let's, put the lab in Gran Sasso, far underground. Let's try and keep items that are not part of the subsystem I'm interested in away from influencing it. Or where I can't do that, let me try and set up a situation where those outside influences can be well approximated or mitigated without having to know the precise configuration of all the things that are on the outside, right? That'll make it impossible. And the importance of the existence of such quasi-isolated subsystems was something that Einstein insisted on as a practical matter for doing physics. And this is in a passage I'm sure many people who are familiar with, but again, it's a nice observation of Einstein, or anyway, a very clear one. And so I'll just give you this passage. It's from a paper he had on, I don't know, physics and reality or something. And again, just read it if anybody hasn't read it. If one asks, irrespective of quantum mechanics, so notice we're not talking about quantum theory here. If one asks what, irrespective of quantum mechanics, is characteristic of the world of the ideas of physics, one is first of all struck by the following. The concepts of physics relate to a real outside world. That is, ideas are established relating to things such as bodies, fields, etc., which claim real existence that's independent of the perceiving subject. Ideas which, on the other hand, have been brought into as secure a relationship as possible with the sense data. It's further characteristic of these physical objects that they're thought of as arranged in a space-time continuum. An essential aspect of this arrangement of things in physics is that they lay claim at a certain time to an existence independent of one another, provided these objects are, quote, situated in different parts of space. Unless one makes this kind of assumption about the independence of the existence, the being thus of objects which are far apart from one another in space, which stems in the first place from everyday thinking, physical thinking in the familiar sense would not be possible. It's also hard to see any way of formulating and testing the laws of physics unless one makes a clear distinction of this kind. Notice, well, here's the end of it. This principle has been carried to extremes in the field theory by localizing the elementary objects on which it is based and which exist independently of each other, as well as the elementary laws which have been postulated for it in the infinitely small four-dimensional elements of space. The following idea characterizes the relative independence of objects far apart in space, A and B. External influence on A has no direct influence on B. This is known as the principle of contiguity, which is used consistently only in the field theory. If this axiom were to be completely abolished, the idea of the existence of quasi-enclosed systems, and thereby the postulation of laws which can be checked empirically in the accepted sense, would become impossible. All right. Now, notice, I mean, there are a lot of things about that passage. Everybody who is not putting quantum mechanics aside and is thinking about quantum mechanics ought to be saying, yeah, but it actually doesn't work that way because of entanglement, because of the entanglement of distant systems is not what Einstein here is saying is that in the field theory, and he means classical field theory, of course, you have locality in both the ontology, that is, the state of the field in one space-time region can be specified completely independently of any mention of the state of the field anywhere else. And you have complete locality of the laws. That is, just given what's going on in one small four-dimensional space-time region, you can tell, I mean, there's a fact about whether that obeys the field equations or not. The field equations themselves are local. And so this, Einstein saw this push toward locality in both the ontology and the dynamics as the tendency of physics and fully realized in classical field theory. And of course, in quantum mechanics, you're now going the exact opposite direction with entanglement between distant systems, because you're now saying, no, I really can't specify the physical state of this subsystem without mentioning the physical state of whatever it's entangled with. That's not, again, that's an issue. Einstein thought it was so serious, and that's what he says here, is that if something like that didn't obtain, it's not that you couldn't have physical theories, but you couldn't have testable physical theories. And his thought seems to be, well, look, if I can't have a quasi-isolated system in a lab, if to make a prediction about what's going to happen to this system in the lab, I have to account for everything else in the universe, then I just won't be able to do it, right? The theory may be perfectly well defined at an abstract level, but it won't be an empirical theory. It won't be a theory that can be used to actually make predictions and test the theory. Now we know that's not quite right because quantum theory isn't like that, but quantum theory is testable. And we do test it, and we run experiments and so on. So even though that chain of reasoning that Einstein gives seems quite cogent, we know there must be a way around it. We've actually managed, in the face of entanglement and non-locality, to make predictions and test and check them. Okay, so the question is, how do we do that, right? What's actually going on when we look at physics as it's actually done? All right, so as I say, if you start with this Laplacian, Boškovićian picture of making predictions by thinking real hard, right? By having the initial conditions of the entire universe or boundary conditions of the entire universe and dynamics given in terms of differential equations and then thinking real hard. That's not what we do. So it's refuted by actual practice that is what we do because we do manage to make predictions and we test them. And so the question is, what are we doing? Right? How does that work? And it's a very straightforward question. I mean, this is not a subtle question. It's not tricky. It's just, and it's not restricted to present day physics. I mean, we tested Newtonian gravity. We tested Maxwellian electrodynamics. We were somehow able to get empirical predictions out of those theories as stated and go into the lab and collect what we consider to be relevant observational data. And so the question is, how do we do it? Now, in terms of the problem of non-locality that I just mentioned in quantum mechanics, where the locality condition that Einstein gave in that quote just doesn't hold, probably everybody here is going to say, all right, well, then I just trace out over the rest of the universe and I get down to a reduced density matrix for the subsystem. And I use that to make the predictions. So I don't need to know, in a way, I don't need to know the precise state of the rest of the universe because instead of the thing that the theory says is the fundamental physical condition, which is the quantum state of the entire universe, I can somehow get this reduced density matrix that I ascribe only to the subsystem. And it's true, by doing that, I get rid of the problem. I also go from what might be theoretically a deterministic theory to a thing that's now only going to give me statistical predictions anyway. Right? So the precision of the predictions goes down, and I replace categorical predictions of exactly what will happen with statistical predictions of probabilities. And then you say, well, whatever's going around in the environment that I'm not taking account of, that won't affect these statistical predictions. That's the hope. It's basically on that hope or whatever assumption that people think, well, there can't be signaling, the no signaling theorems come in. All right, I'll leave that aside now. So you might say, all right, that one problem that's going to get in our way is the non-locality. Maybe we can mitigate that by going to density matrices somehow. Another problem was these initial conditions, right? I said, look, I have a box of gas or whatever. I have any large object. How am I going to figure out, even if I'm only looking at this isolated subsystem, how am I going to get my hands on its physical condition, initial physical condition? How am I going to observe if there are many, many degrees of freedom, how am I going to observe them? How am I going to record that? And so on. And you might say, well, sometimes we don't observe it. We actually calculate the initial state theoretically, right? And so you imagine, you say, all right, I'm going to take some atoms and I'm going to cool them down. And they're going to go down into their ground states, and I don't have to observe them. I just figure out, according to the theory, what those ground states ought to be, right? And that clearly mitigates the problem of getting information about the initial conditions. And, it's a little bit of a tricky thing because now you're using the theory itself, but that's fine because you're testing the theory. So you start from the beginning saying, well, assume the theory is correct. If the theory is correct, then in such and such conditions, this system ought to end up in such and such a state. If it's in such and such a state, then according to the theory, if I poke at it in a certain way, it'll do a certain thing. So that, that can help you with that problem. It's not going to help you much with the state of a box of gas at room temperature because it just doesn't, the known conditions that that box is in are not sufficient to nail it down to a single or even a small number of possible physical states. So then something else is going to come in. Anyway, it does help that at least sometimes you can use the theory itself for a small system to calculate what the initial state ought to be according to the theory. In the case of the box of gas, where we can't do that at room temperature, what we can do is say, all right, I'm not even going to attempt to plug in the exact initial state of the box of gas. I'm going to start out with a probabilistic description, a probability measure over the space of states, and say, I don't know at all what the precise initial state of this box of gas is, but here is if it's at thermal equilibrium, here's a probability measure or whatever, even if it's not at thermal equilibrium, if it's in some other state, some other macroscopically describable state, here's a probability distribution over the possible precise states. And then I'm going to use that probability distribution to make my predictions. So again, that might make the calculational problem harder. You might think, well, wait, if I don't even know the precise initial condition, all I have is a probability distribution over all of these possible initial conditions. And then if a la Laplace's demon or Bošković's demon, I then have to calculate the trajectory of each of those possible initial states. And then I'll get a probability distribution over final states. Then you think that's going to make my calculational problem much, much harder because now I have to calculate not just what will happen for a single initial state, but for all of these possible initial states. So then you might say that's going the wrong direction. On the other hand, as we all know, it can also make it much easier. Because you're dealing only with statistical descriptions, it can turn out that the fine details of the specific trajectories wash out. And that's what happens in standard thermodynamics when it's reduced to statistical mechanics, that you end up with statistical descriptions of the initial state, and then it turns out that the statistics of the final state can be calculated to a large degree, turns out to be pretty independent of the fine details of the interactions in the kind of statistical arguments that Boltzmann was giving and so on, and Maxwell was giving. So whether going from a really deterministic calculation to a probabilistic one makes the computational problem harder or easier depends on the details. Then you might say, all right, I know I can't actually do these calculations in any precise way, but I can approximate and I can idealize. So there are a bunch of techniques for taking what is an intractable problem, if I want a precise solution, and arriving at what seem like reasonable guesses for approximate solutions. Um, you can model, I mean, we all know the sorts of things that are done, and this was done even with Newtonian gravitational theory. Nobody knew the precise mass distribution of the moon or the sun or the earth or the planets. But you say, okay, if they were uniform spheres, then I actually have an argument that I can treat them as point particles with the total mass. Of course, they're not uniform spheres, but okay, maybe they're close enough to being spherical and close enough to being uniform that I can take the thing I can calculate as a pretty good starting point and then apply perturbation theory techniques to try to get my hands on how close the actual situation is to the idealized one that I can calculate, right? So I idealize in certain ways to the point where I can actually do the calculation, and then I try to de-idealize, not precisely, but through perturbation theory to get error bars. Right. So that's a way of handling calculations you couldn't do from data you don't have. Um, how well does that work? Well, again, you can't give any general answer here. Depends on the specific theory, depends on the mathematics involved, depends on specific application of the theory. Sometimes you can have very plausible arguments that that's going to work. And finally, and this is really all of this stuff has just been set up because as soon as you ask the question, how do actual predictions get ground out, right? I mean, how do people use physical theories and arrive at actual testable predictions? Um, all of these problems and then gestures, at least at some solutions, I think might occur to you very easily. I mean, I don't think there's anything in the least bit profound or surprising, I hope, about anything I've said up until now. Um, and I'm sorry, I mean, maybe this is going on longer than I had thought. I'm just trying to be careful here. Um, the Now we get to the main point, which is the real topic of the talk, which is how do you treat what we call measurement apparatus? How do you treat parts of the experimental situation that have been put in place to collect data and without which we wouldn't have any data at all? How do they get treated theoretically, as it were? Um, and you might think that this is a problem when, as soon as I talk about measurement apparatus, you might say, oh, you're bringing up the measurement problem. I'm not. I mean, of quantum mechanics, I'm not. This is a much more general programmatic problem, right? Often I'm doing experiments on a small system or a small subsystem for the sorts of reasons we've just given that you can calculate it and predict it and so on. But in order to collect the data, I need a bigger system, right? I need a macroscopic system. I need to somehow get to macroscopic results. That's true independently of any quantum mechanical considerations. Now, there's a very nice quote of Einstein I want to start with here, and it's something Einstein said not about quantum theory, but about relativity. So that might surprise people because you might think, wait, we have all these problems with quantum theory, but surely relativity, that's straightforward, right, in itself. Um, but Einstein was aware that no, it's not that simple. And so this passage I think is extremely important passage. Um, this quote here is, if you haven't heard it, I hadn't heard it until recently. It's actually a quote from Schrodinger in his original papers on the wave mechanics, and he talks about how he was inspired by de Broglie and by some brief but infinitely far-seeing remarks by Einstein. And I love that brief but infinitely far-seeing remarks. It seems to me it applies to this passage too. It's a short passage. It makes a point. It's an extremely deep point. So this occurs, by the way, in the autobiographical part of Albert Einstein, Philosopher, Scientist, the Schulp volume, when Einstein is just doing his autobiography and explaining what he did. And as part of it, he gives a little overview of special relativity, a kind of standard looking introduction to special relativity. And when he's done with that, he then says this. He says, first, a remark concerning the theory as it is characterized above. One is struck by the fact that the theory, except for the four-dimensional space, introduces two kinds of physical things. That is, one, measuring rods and clocks, and two, all other things. For example, the electromagnetic field, the material point, and so on, right? And you can imagine what he's done. He's done the usual thing when you present relativity. You talk about the behavior of clocks and rods, when doing what? When measuring, trajectories or whatever of particles and the behavior of fields. This, in a certain sense, is inconsistent. Strictly speaking, measuring rods and clocks would have to be represented as solutions of the basic equations, objects consisting of moving atomic configurations, not, as it were, as theoretically self-sufficient entities. Again, what the Laplace demon and the Bošković demon are able to do is not do that, right? They're operating from beginning to end with just the elements in part two, right? The electromagnetic field and the points and the fundamental equations, and calculating what such a system will do according to the fundamental dynamical laws, right? So there again, this kind of background in the back of your head, Laplacian picture will completely mislead you, because you'll miss exactly the point that Einstein's making here, right? So he says, right, strictly speaking, of course, that's what measuring rods and clocks have to be, right? They have to themselves be just physical objects, not, as it were, as theoretically self-sufficient entities. However, the procedure justifies itself because it was clear from the very beginning that the postulates of the theory, and this is just relativity, are not strong enough to deduce from them sufficiently complete equations for physical events, sufficiently free from arbitrariness, in order to base upon such a foundation a theory of measuring rods and clocks, right? So there's the measurement problem in relativity. It's not the kind of measurement problem we have in quantum theory that arises from the linearity of the Schrödinger equation, and we're all familiar with. It's a much more simple thing, that in order to actually get to empirical predictions, you've got to stick in the rods and clocks, but you don't treat the rods and clocks using just the resources given by the theory, right? And he said you couldn't, because of course, relativity just didn't, at that point, they just didn't have any theory of matter that could handle solids, right? Or, matter, normal matter as we think of it. All you had was the stress energy tensor. If one did not wish to forego a physical interpretation of the coordinates, something which in itself would be possible, it was better to permit such inconsistency, right? He said, look, this is the way we had to go forward, with just making certain assumptions about how the clocks and rods behave without justifying it from fundamental physics, with the obligation, however, of eliminating it at a later stage of the theory. But one must not legalize the mentioned sin so far as to imagine that intervals are physical entities of a special type, intrinsically different from other physical variables, reducing physics to geometry and so on. Now, there's a lot one could go in about the meaning of that remark that would take us into different interpretations of relativity. That's not my point here. My point is that is Einstein's observation that even in relativity, and where we sort of normally think there are not deep conceptual problems that correspond to the deep conceptual problems in quantum theory, he says you have this problem getting actual predictions out of the theory. The predictions had to be about macroscopic things like clocks and rods, but you couldn't treat them in a principled way given the fundamental postulates of the theory. And I think that's correct, right? I think he's absolutely right about that. And then you have to think about, all right, what was this sin? I had to, as it were, write out a promissory note. I had to make some assumptions and write out at that time a promissory note. Sometime in the future, when I'm able to, I need to justify these assumptions. But I need to make them now, because without them, I'm not going to get any predictions out of the theory at all. So people might say, oh, but it's not so hard. Actually, even from the fundamental principles of the theory of relativity, you can make predictions about behavior of clocks and measuring rods. Now, the measuring rods part, let's leave aside, but let's take the clocks, because this is, everybody's going to be familiar with this. How do people do this? I mean, Einstein says, no, you can't do it. Or at least he couldn't do it. But what's going on? Well, the matter part in relativity is just represented by a stress energy tensor. That's it. And given that stress energy tensor, that's all you needed to feed into the fundamental equations of general relativity in order to solve for the space-time geometry. But that's not, all of that is not about macroscopic matters of fact, right? Certainly not about conscious experience. And so the gap between what the theory explicitly trades in, like the geometrical structure of space-time and the stress energy tensor. I mean, think about exactly what goes into the Einstein field equations. That gap is filled by a hypothesis about actual physical clocks and rods, even though no physical theory of the exact constitution and dynamics of the clocks and rods existed. Okay, so those assumptions about what the clocks and rods do were not backed by a physical argument from fundamental principle. Now, sometimes you might think, well, you can at least do it with the clock. And this is what happens, and everybody knows this. Oh, what about a light clock? Right? Can't I get from the fundamental principles of relativity the behavior of clocks by analyzing light clocks? And you're all familiar, I take it, with a light clock where you've got two mirrors that are parallel to each other at a fixed distance and a light ray that's bouncing back and forth between them, and a counting mechanism that somehow manages to keep track of whenever the light ray hits one of the mirrors and counts, right? And this is in every book, right? Why? Because, well, at least under easily statable assumptions about how the light reflects off the mirrors and so on, you can say, count the number of clicks there would be in such a clock. As long as the clock is inertially moving, it's an ideal kind of thing. The mirrors are supposed to be essentially, heavy enough that there's no effective rebound, and the whole thing is not being accelerated, and the clock is inertially moving. You can then make calculations about what this clock would register in terms of the number of beeps or bounces that it counts. But what's wrong with that? Well, first of all, actual clocks are almost never inertially moving. So even if you did that, you're going into an idealized circumstance, which is not the actual circumstance. But that's not the main point. The point is that nobody's ever constructed or used such a clock, right? That's not how actual clocks work. Actual clocks are not light clocks. They're nowhere near to light clocks. They're not even approximations to light clocks, right? So the reason why people talk about light clocks was that you could kind of analyze them with certain idealizing assumptions. And that was nice, because then you could say, oh, this is what a light clock would say, would register. But in doing so, they lost complete contact with the actual clocks that actual physicists and humans have ever used, right? Because they just don't work that way. So it's a weird situation, right? If what you're worried about is how do I make predictions for what's going on, what I'm going to see in a lab, doesn't do me any good to analyze a light clock because I'm not going to use a light clock in the lab. It's even worse with rigid rods. I don't want to go into rigid rods except in to say the right thing to do if you're analyzing relativity is to get rid of the rigid rods altogether and just use clocks and light rays. You can do that, right? You can replace the rigid rods with light rays and talk about transit times and radar ranging and so on. For many reasons, again, one is that rigid rods are really hard to analyze. And the other is they're not what we use anyway, right? I mean, we think we have a pretty good idea of how far the moon is from the Earth, not by taking a ruler and, going hand over hand and going from here to the Earth and counting, which is a sort of way that you use rigid rods in these kind of pedagogical presentations. So the right thing to do with relativity is just not even to deal with rods. It's get rid of them, talk about light rays, talk about clocks, but you still have the problem of the clock. So now we're back to the main question. How does actual physics work? It's not by application of the fundamental physics to a situation and analyzing it, even with idealizations, using just the principles of the fundamental physics. That's what Einstein said about his presentation of relativity. He was right. So how does it work? Okay. It doesn't work that way. It's never worked that way. It's never worked in the Laplacian way. It's never worked in the Boškovićian way. How do we get testable predictions from a theory? And notice the scare quotes around derived, because in a way, the claim is you can't derive these in the way suggested by the Laplacian rhetoric. Now, once you put it that way, I don't think the answer is that hard. I think the answer is kind of staring us in the face, but we haven't appreciated it. And that Einstein's remarks about relativity provide a useful model. As I said, that in relativity, if you give me a global stress energy tensor, the field equation will then restrict the space-time geometry, right? It doesn't give you a unique one, but let's not worry about details in relativity. Given an initial stress energy tensor and the geometry of an initial Cauchy surface and the external curvature of the Cauchy surface, how it's embedded in the space-time, you can present general relativity as an initial value problem entirely mathematically analogous to the one that inspired Bošković or Laplace, right? Thinking about Newtonian mechanics. Even if I give you all that, which again, for various reasons you could never have, you still have no predictions about the observable behavior of clocks and rods, right? All you have is a solution that gives you the geometry of space-time. So how do we fill that in? Well, it's easy in a way. You make a certain assumption and you issue it together with a promissory note. Here's an assumption. Actual physical clocks measure approximately the proper time along their trajectory, right? So that's an assumption. The actual space-time stuff that you get out of solving the general relativistic field equations does have proper time. And if you say the clock is traveling along some trajectory through it, there is a proper time associated with that trajectory. That you get right out of the physics. The assumption is that that's what the clocks measure, approximately, right? That the reading on the clock that you can actually see and record will be very close to, proportional to the proper time, right? And you say that, and you say, but why should I believe that about actual clocks? And I mean, there are various reasons you might think that's the right thing to believe about actual clocks, but certainly not because you can prove it from a physical analysis of clocks. You can't. Now, what kind of reasons could you give for thinking this is a reasonable assumption to make? Well, you could notice, for example, that what we consider to be well-made clocks all agree with each other. And because they all agree with each other, it seems as though they're all measuring something, right? That they're all tied into some single thing that's out there in the world. And if you're starting with relativity, about the only single thing, frame-independent objective quantity in the neighborhood is the proper time, right? So it's a reasonable assumption to make. And of course, it's going to be approximate. You're going to say from the beginning, any actual clock isn't going to exactly give you the proper time. It's not even clear the proper time of what, because you'd need a point-like trajectory. Okay, but I think everybody can see how, all right, there are things around the edge here to be clarified. Now, how does this work? Well, it's clear. If I grant these assumptions, then I can make approximate testable predictions from the basic postulates of the theory. I use the basic postulates of the theory. I use some idealized model of the initial conditions that I can solve, and maybe perturbation theory, to give me an approximate space-time geometry. That gives me at least approximately the proper times. And then with the assumption that actual clocks register proper time, now I can make predictions about what the actual clocks will show, right? And if those predictions turn, now you might say, yeah, but okay, but why should I believe this assumption you're making about these clocks? You're adding this assumption. Why should I believe the assumptions that these approximations are good? Why should I believe the perturbation theory and so on when I can't actually do the calculations? Why should I believe the approximations? Now we get the usual observation about holistic confirmation. If those predictions turn out to be correct or, accurate within error bars, then holistically, that's reason to believe that all the essential parts that went into making those predictions are probably pretty, are reasonable, maybe pretty close to being correct. Why else would you be getting good predictions out of this whole gadget if none of the parts that went into making the predictions, right, if some of them were fatally flawed in some way? Now that you can say that's not absolutely convincing, and it isn't absolutely convincing, but it's pretty convincing, right? It's pretty good reason to take this theory seriously if from the fundamental postulates, together with approximations like these, together with these assumptions about clocks, you actually get predictions that work. Okay? That seems to be the methodological situation. Even if that's true, that's reason to think that the theory at least is on the right track or something like that. You still have this promissory note that you issued with respect to the macroscopic instruments that in the future, you better try to explain why the instruments do work in the way that you're asserting that they work, because you haven't justified that, not from fundamental physical principle. If you can never do that, then you're in real trouble. Of course, you may recognize that that's kind of a project for the far future. I mean, for Einstein in 1905 or in 1915, it was for the far, far future because they didn't have any decent theory of matter at all. None. So it had to be a promissory note. Okay, but that's how physics works. Now, all of this, which I hope actually is not controversial, I'm now going to give an application to the present day situation in quantum theory, and particularly regarding people using pilot wave types of approaches to understand quantum theory. What I want to claim is that the situation now is exactly this situation. And one has to recognize that's where we are if you're going to discuss how to make predictions and how to test them. Because we still have no actual theory of how any measurement apparatus works, right? Physical account that could be used to demonstrate, even by approximation and cutting corners and so on, why these macroscopic instruments produce the output that they do. Now, in the pilot wave theory, I want to talk about the pilot wave theory because that connects up to this discussion in a very direct way. I claim exactly this logic is used, and again, without people noticing they're doing it, in discussions of quantum theory. Um, and certainly when one's introduced to the pilot wave theory. So the first thing you do in the introduction when people are trying to explain how the theory works is, of course, you talk about the two-slit experiment and you get pictures like this. I mean, this is the classic picture. It's things you could say about that that are not relevant here. But everybody, I hope, has seen this. These are supposed to indicate mathematically possible trajectories of a single particle in a two-slit apparatus where the particle has managed to get through one of the two slits. So it's either entering through slit A or slit B, shown on the left, and proceeding toward the right. And it will be moving around according to the guidance equation and given the solution to for what the wave function is going to be. And this is just showing you the different trajectories. And what always happens is people do this, they show you this, and they say, look, this picture explains why you would expect to see interference bands when you do a two-slit experiment and repeat it many times. The additional, now, what do you mean explains? Well, what are the other assumptions that go into this? One assumption, which is obvious, is that in some sense, each time you do the run, you're making a pretty random selection among these possible initial conditions, right? Which in this case is just the initial position of the particle. It's somewhere in slit A, somewhere either in slit A or slit B, and maybe a pretty flat distribution across there, right? No reason to think it's more likely to be toward the middle or, the 1/3 mark or whatever. So you put a pretty flat distribution for the initial position over the gaps. But then there's another assumption that everybody makes and nobody mentions, which is that this is the actual calculation for a single particle propagating with this wave function, and that's it, right? There is no screen in this. There's no interaction with a screen. That's not been put in. It's not been calculated if it had been put in. This is just the free motion of those particles. But everybody looks at that and says, oh, that would explain the data. Why? Well, they're making an assumption. They're making an assumption, which is easy to state, that where the marks appear on the screen will be at least very close to where the particle would have been without the screen. Right? If you don't make that assumption, there is no connection between this calculation and actual data. And if you do make the assumption, there is a connection. Now, of course, you admit that you're not proving that that's true by analyzing the screen physically. You're not attempting to. You're making the assumption that the mark forms, and again, you're not making the assumption the mark will form exactly where these trajectories are, because everybody knows the screen will have some influence. I mean, it's a physical object. It's going to change the physical situation. Nobody's denying that. So what are you? You're assuming that whatever influence the screen has on the trajectories, it's not too big, and the mark is going to appear somewhere in the vicinity of where the particle arrives. Now, I mean, here are the points that I'm just making, that when you see that picture, no attempt has been made to physically model a screen. No attempt has been made to explain why marks form on a screen. Nonetheless, everybody thinks that what you have shown is relevant and kind of explanatory of the actual data, which shows these interference bands. And again, it's not because people think screens are magical, that they're not physical objects, that there isn't a physical story to be told of how the marks form, even though they're not doing it here. So you just say, all right, so what are they assuming? They're assuming that, yes, there will be adjustments made because of the presence of the screen, but they won't be too big. This strikes me as a perfect analogy to what Einstein says about relativity. Actual clocks will not actually measure the precise proper time along the trajectory. I mean, there's not even really a trajectory because the clock is not point-like. right? An actual clock is spread out. So, what do you mean the proper time along its trajectory? All right, so there are all these things, but you say, yeah, okay, idealize it as a point, right? Take your actual clock, idealize it at a point, and idealize it as somehow pretty closely measuring the proper time along that trajectory. That's what you do. That's how you make the prediction. Yes, it has these logical gaps that need to be filled in later. But if you don't make an assumption like that, you're not going to make any predictions at all. I think it's precisely analogous to this case. What do we end up with? That assumptions made about the screen, together with these promissory notes that are issued when we make them, right, are that A, although the presence of the screen will have an effect on the trajectories, that effect will be relatively small. What do I mean by relatively small? Okay, I actually need, and I could empirically check some of this. Although no physical account at all of the interaction between the screen and the particle has been provided, we assume that the mark will form very near to the location where the particle reaches the screen. So there are two issues. How much does the screen deflect the particle from where it would have been without the screen? And how close does the mark on the screen, how close is that to the actual location where the particle reaches the screen? We need to assume that both of those are relatively small to make this prediction. If we grant them, then we get approximate predictions follow. Now, here's another very nice, again, you might say brief but infinitely far-seeing remark by Bell that again, he's not making this point, but it's implicit in this point. So this is from Six Possible Worlds of Quantum Mechanics. Again, when he just starts to try to explain the way the pilot wave theory works, the last unromantic picture I'll present is the pilot wave picture. It's due to de Broglie and Bohm. While the founding father agonized over the question particle or wave, de Broglie, 1925, proposed the obvious answer, particle and wave. Now, it's this last part. Is it not clear from the smallness of the scintillation on the screen that we have to do with a particle? And is it not clear from the diffraction and interference patterns that the motion of the particle is directed by a wave? Now, think about the first thing. He says, look, the fact that a little dot, a particularized located little dot forms on the screen, which is, we know empirically happens, doesn't that suggest, he says clear, you could say very strongly suggest that there is some small item, right? Some small, not directly visible item that reached the screen, that hit the screen, right? That provoked the formation of this spot where the particle itself reached the screen. Now, of course, you could imagine a theory where that's not true. In a spontaneous collapse theory, that's not true. In many worlds, whatever it does, it's not that, right? There is no particle that reaches the screen. Whether there's a screen, okay. There are all kinds of questions here. But Bell's point is that if you postulate particles which have definite locations, that the idea that the spots you're seeing on the screen directly reflect the locations of those particles before they hit the screen, that's the natural assumption. Of course, you can demand that there be a more detailed theory of how that works. And maybe until you have it, you can harbor a certain amount of reasonable skepticism. Who knows? Maybe if you actually try to model the screen, it'll turn out the spots form 8 inches to the right of where the particle reaches the screen. You can't rule it out. It seems kind of crazy, right? Doesn't sound very plausible. But just that sentence, is it not clear from the smallness of the scintillation on the screen that we have to do with a particle? That inference is backed by exactly these kinds of assumptions about how screens work that are not based in any fine analysis of any physics. They're just, you got little dots, they're probably little things. And the dots are reflecting where the things went. Why is this so important, right? So I've been going on and on. Maybe everybody's bored. I don't think anything I've said is controversial. The importance of it is the way this gap between what you can cleanly describe using the mathematical physics and the actual empirical predictions, right? There's a gap there. If it's being filled by the kinds of assumptions that Einstein indicates and that I've indicated here about screens, then that is going to be very important because a structurally, and here's kind of the operative paragraph that maybe people go nuts over, structurally identical account can be given of how to get approximate predictions for observed arrival time distributions out of a theory like this. Not just where does the spot form on the screen, but when does the spot form on the screen, right? Structurally identical given the kind of reasoning that's being given. You say, look, I'm just going to assume the spot forms pretty close to where the particle hits, and the particle hits pretty close to where it would have gone without the screen there. And now I say, I'm going to assume the spot forms pretty close to when the particle arrives, and the particle arrives pretty close to when it would have arrived at that location without the screen. It seems to me that those arguments structurally are exactly the same. And if they are, then the very basis one uses to make position distribution predictions out of this theory can be used to make time distribution predictions out of the theory. And if you raise serious doubts about the appropriateness of doing it in the one case, I don't see how you avoid having to raise exactly as serious doubts about the appropriateness of doing it in the other, which would mean that you then doubt whether the theory can even make the right predictions about the two-slit spatial distribution. I myself just don't see any way around this. Now, of course, I'm claiming an analogy here between predictions of spatial location, predictions of time. Formally, I'm saying you just treat them the same way. Now, someone might say, no, 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 somehow space comes into this in a very different way than time, so that some of these assumptions are appropriate for space, but not for time. I don't know. I mean, there are lots of logical possibilities here. But at least that the initial situation ought to be to recognize that these kinds of approximations or assumptions are made from the beginning in getting any empirical predictions out of the theory. Now, this is, of course, very important, and I'll just mention this, people know this. In the standard approach to quantum theory, where you associate observations with Hermitian operators or positive operator valued measures mathematically, the case of space and the case of time are entirely different because there are Hermitian operators for position and no time operator. And if this problem were solved by the postulation of these operators, then there would be a very different situation, because in the one case you have an operator, in the other case you don't. But what I'm claiming is that it was never solved by the postulation of operators, right? The way you got to the actual predictions was through these assumptions about what screens do, or, as in relativity, assumptions about how clocks work. And that didn't go through, oh, but it must be such and such an operator in order to make this assumption, right? I need a certain operator to assume that spots form about where the particles arrive. No, you don't justify that by anything except saying it's a screen, and a dot's forming. And in my theory, I actually have an arriving particle. I'm going to assume that dot's forming where the particle got there. So if that's right, then the way one would make arrival time predictions, again, they're going to be statistical distributions for arrival times because you don't know the exact initial conditions, you don't know the exact particle locations at the beginning, but in the normal way you make statistical predictions, you would have you could make statistical predictions about where the spots will form. You can make statistical predictions about when the spots will form. You can make statistical predictions actually about joint distributions of where and when spots will form under these assumptions. As I say, you don't do it via Hermitian operators or POVMs for the time, because there aren't any. Nonetheless, these are things we think we can observe, right? You can literally go into a lab and collect this data. And I mean, it's maybe also worth noting, I have at the bottom here, this connection between the theory and the data from the beginning has been weird. I mean, you think about the way Bohr talks about making position and momentum measurements. And he says, oh, to make a position measurement, I need a screen and I need to fix it, right? I need to nail it down somehow so it gives me a position reading. But if I want to measure the momentum, I take the screen and put it on springs and somehow measure the recoil. And you're going, no, you don't. That's not what you do. As a matter of fact, that's not how you make what you call a momentum measurement, right? In actual physics. This was not, this just isn't actually the way it's done. Certainly not for particles, in the LHC. It's a tempting kind of thing to do because it's theoretically, you kind of can understand what he's saying. But then when you just stop for a minute and say, wait, is that actually, it's like the light clock. It's nice to talk about light clocks because I can analyze them, but it's stupid to talk about light clocks because nobody uses them. So if you can have a theory that can make predictions about light clocks, but not other clocks, it has not made any predictions that have ever been tested. Now we're coming to the end. I'm sorry if I went late. I hope these things will be obvious. They have not been obvious over the 100 years since the initial suggestion of a pilot wave picture. There are methodological advantages to a theory that actually postulates particles or small objects that have locations, or at least very pretty good approximate locations. I mean, little lumps in fields moving around are fine. They would have the same methodological advantages to having particles, but localized objects, right? Well localized objects. By having that in your ontology, then you have trajectories of these things. And these small localized things, I mean, let's just call them particles. They exist at any given time in a certain place. They have usually continuous trajectories. All of that is now given to you by the theory. And then all you need are these idealizing assumptions about screens and clocks, that the marks on the screens, are formed about where the particles hit them and formed about when the particles arrive at them. That piece of the ontology allows you to introduce an idealizing assumption like that and use it to make predictions. If you don't have localized objects like that, then these assumptions would do you no good, right? If nothing local arrives at the screen, then saying that the spot forms near where the thing arrives, that doesn't have any purchase, right? Just doesn't help you. If there isn't a time when a local thing arrives near the screen, then you can't say I'm going to explain the observed time distribution in that way, because there's nothing to glom onto, right, in the theory. And that's really important because we want to make connection with actual recorded data. If we don't make connection with actual recorded data made by not by light clocks and not by measuring momenta by screens with springs on them, right? If we actually want to connect with the actual data actually collected in real labs, it seems to me we need to use these kinds of methods that Einstein pointed out needed to be used already in relativity. And really needed to be used, I mean, if you go back, the same for Newton and so on. I mean, nobody's ever analyzed macroscopic experimental equipment from fundamental physical theory. Can't do it. So you stop and say, okay, but what was done? Something was done. Something was done that allowed you to make predictions. What was it? I think this is the story of what it was. Of course, if this is right, then you're issuing these promissory notes whenever you make these assumptions. And the promissory notes are sitting there, and you would hope that you could move forward with a proper physical analysis of how a particle interacts with a screen or whatever that will end up justifying, from a theoretical perspective, the assumption that you did at the beginning. As I said, even absent that analysis, one can say one has good reason to believe that the assumptions are pretty near correct, just if the predictions come out right. That's this kind of holistic confirmation theory, because you have a whole bunch of assumptions that jointly are making predictions. Predictions turn out to be right. That gives you some reasonable epistemic boost of confidence in all the essential assumptions that went into making the prediction. Now, as I say, if we now at the very end kind of focus down on quantum theory, not every approach, as we know, for accounting for quantum phenomena postulate the existence of particles or of identifiable local things, or even local fields with lumps in them that move around. The GRW theory doesn't do that. Not with the flash ontology, not with the matter density ontology. You could have a GRW-like dynamics with a particle ontology, and you feed the wave function as given by the GRW dynamics and use it as a guiding equation for particles. You could do that. I don't know if anybody's ever done it, but then at least you'd have the particles that you could appeal to for putting in these assumptions about screens and so on. In many worlds, it's never had a clear local ontology at all of any sort. Certainly not one with particles, and just the opposite. People like David Deutsch keep claiming rather ridiculously that the particles play no interesting role in the pilot wave theory, which is, I mean, this is just wrong, right? It's not a thing an adult ought to be saying, but he's been saying it forever. I don't know if he'll ever stop. But I hope this illustrates a very precise way that the particle ontology plays an essential theoretical role in the way this theory is understood and the way it's used to make predictions. And that if you try and just eliminate the particles, right? The many worlds line is that all the particles do is they're pointers that point to a branch of the wave function. And you say, no, they're not. No, they're not. That's not what they're there for, right? They're not there for to pick out a wave of the wave function and then you analyze the wave function to get you the predictions. No, absolutely not. That's not what's going on. And I hope this is a very concrete example of what is going on. And so I would say, if nothing else, again, it doesn't mean everybody has to suddenly believe in pilot wave theory, but you should appreciate the methodological advantages that accrue to a theory that has things like particles with continuous trajectories. You can't make your predictions in the way I just sketched. And so, if nothing else, you really have to explain how you do make predictions, even using these kinds of approximations or assumptions or whatever. I don't care. I'm not saying you have to derive it all from fundamental principle. That wasn't done here. But at least you understand what assumptions are being made. You can clearly state what they are. And you can clearly state what the promissory notes are. And that's that, okay? That's the end of that story. So that was kind of, to me, all of the recent discussion that many of you are familiar with about the arrival time problem is what provoked me to think about this. And in a way, I hadn't. I mean, even though I think all of this is very obvious once you lay it out this way, it hadn't occurred to me. But once you start thinking this direction, I don't see any other way it can go. And so that was what I wanted to talk about today.
Thank you, Tim. Thanks for this very interesting talk. So yeah, we have a couple of minutes still for questions. So why don't we just go ahead with those? So everybody is still applauding here. I see all the hands up here. Okay, but there are also several questions, so let's start with a few of them. Jan, you were the first. You're still muted, I think.
Thank you. Okay, hi. So thank you for a very nice talk. Just one remark regarding this asymmetry between treating position and time measurements in the double slit, right? So I think I would. To me, it seems like an argument could be made for the asymmetrical treatment by the way how the detectors work. By the way, I'm sitting up behind in front of a double slit, Bohmian double slit setup where we measure actually Bohmian trajectories of photons. So this is a topic close to my heart, I would say. The point is that in your picture, right, the wave function of the photon was dislocated transversely a lot. So the detector had the resolution of the detector was far below the size of the wave function. But typically, when you do the measurement in time, the resolution of your detector is not really able. I mean, you have your wave packet which guides the particles. The wave function is longitudinally, has some length, and it has a velocity with which propagate. And the time resolution usually of your detector is not able to resolve where there is. So there is the completely asymmetrical situation how the detector handles this. So therefore, I would say it does not really matter to model how the detector interaction works in the position case, because you can safely assume, as you say, it won't change much. It might change a little bit. There might be some light back action, but it will be more or less the position which is theoretically ideally predicted. But since the resolution is so low, the detector back action might be really important to determine really the number you see when you do a time measure.
Yeah, I mean, so this is where you know and I don't know the details, and I completely accept everything you just said. Taking that on board, at least one should point out, if that's the situation, if the real difference between the spatial predictions and the temporal predictions is in the time resolution that the instruments can give you, for example, then you would say, wow, here's a really important question. How much can we reduce that uncertainty, right? Can we go down to femtoseconds? Can we, what is the actual on the ground experimental situation? And at what point would the resolution become sharp enough that the worries you have you wouldn't, you would see more of an analogy between the two cases. I mean, for me, what's really exciting about this, what's just unbelievably exciting, is the idea that actual experiments done in the lab and not at the LHC, right? Not high energy, just the opposite, right? Very low energy, high precision tabletop experiments could in principle produce data that could be used to severely test different fundamental approaches. I mean, that's kind of the holy grail we've had, is we have all these different approaches to understanding quantum phenomena, and then everybody says, oh, but they make essentially the same predictions, and we can't decide between them on straightforwardly empirical situations until we get, a collider that's bigger than the entire, galaxy or something, right? To get up to some energy scale that the high energy people will think becomes relevant. So yeah, I don't know enough about, and I understand everything you just said, and I don't know enough about the experimental situation to comment on it. I just think it's extremely interesting that at this level of discussion, the details of what we can do experimentally in a lab on a tabletop become relevant, right? Even if it turns out, okay, we actually can't get the time resolution we want. I mean, I shouldn't say nobody has been thinking about that. I spent my life thinking about this stuff, and I never thought about this stuff, right? Until this arrival time issue was brought up. And so to me, that's very exciting.
Thanks.
Thank you. So next question is by Margarita.
Okay, thank you very much. Yeah, so I was interested in the relationship between the quantum measurement problem and the more general measurement problem you're raising. because there is a tradition that sees the quantum measurement problem as being the problem according to which the measuring process, the measuring apparatus figure as primitive in the theory. And I don't know if you agree, but it seems that what you're saying is that this is a feature, a more general feature of a problem of empirical coherence, as some call it, or cognitive stability, that we have to ensure for any theory, not just for quantum mechanics. And so we can do that in different ways. And some parts of the measuring process or measuring apparatus and its working will remain a primitive assumption in the theory, but we can differentiate between better analysis or worse analysis of how this will be spelled out. Sorry, it wasn't very clear, but.
Okay, so let me make a comment about that. Obviously, there's this thing called the measurement problem that only got that name because of quantum theory. And there are different ways of characterizing what it is, right? In some ways of characterizing it, it's very specific to quantum theory. So if you say, look, here's a problem. Suppose I think the wave function is complete and it never collapses, and because Schrodinger's equation is unitary, right, and linear, then I set up these situations, Schrodinger caddy kind of situations, and say, I don't know what to make of this. I mean, Lev knows what to make of it because he's a many worlds guy. But if you're not a many worlds guy, you don't know what to make of it. That's a very specific problem to quantum theory and requires both the completeness of the wave function and the linearity, the evolution, to even have that problem. The problem I'm talking about is much more general. There's also this problem of theoretical incoherence, right? What if you have a theory that the theory literally undermines the possibility that you could have good evidence for the theory, right? This is the kind of problem that David Albert talks about. That's sure a problem, but I don't think that's a problem here. No one's suggesting, I mean, it would be a problem if you could prove that the theory could not model screens and clocks that approximately did what we're assuming they approximately do, right? If you had an argument that the theory itself rules out such things, then you'd be in deep trouble. But I don't think we have any such argument here, right? The hope is that getting further and further along and being able to apply quantum theory to solids and to screens and so on, that we can get more and more articulated accounts of how these screens work and maybe how much the particle might be delayed or moved to the side or, in a pilot wave picture. I don't see this kind of self-undermining to be a problem here. It's rather more the thing Einstein was talking about. It's just right now we can't provide the theoretical analysis of the macroscopic equipment. We just can't. Not because it's, as it were, in principle impossible, right? I mean, maybe Laplace's demon can do it. I don't know. But we can't do it. So how do we fill that gap? We fill that gap through plausible looking assumptions about how these pieces of apparatus work, with the promissory note of trying to justify better those assumptions as we can better analyze that machinery. So I think there are other issues that come under the name the measurement problem in quantum mechanics that are much more specific to quantum mechanics. And that's why I think, I didn't even want to get into quantum mechanics except at the end, because I think this problem occurs everywhere and always has occurred everywhere in physics.
Okay, thank you.
Great. So let's go on with the next question by Hermann Batelan.
Oh, Paula, please allow me one sentence, because, or a little more than one sentence, because I have to run to my student seminar now. So I would propose the following. So first, Tim, thank you so much for this talk, but I have to really go to my next seminar. I'll transfer the host to Fabian. I'll keep the recording going, and because I think it would be nice to maybe continue a little bit this discussion, because it could get a little bit beefy now, and I would like to watch that later on. Okay, so from my side, I have to say goodbye. Tim, thank you very much. Fabian, I hand off the host to you, and I hope the recording will continue. All right. Bye-bye.
Hi, Dirk. Okay.
Okay,
Let's
sure.
continue with your question, Herman Batelan.
Yeah. So, first of all, thanks, Tim, for an enjoyable presentation. I could only come in halfway because I had another meeting before this, but all the things you say, I enjoy a lot. And I want to just state that I'm supportive of efforts where people, theoreticians, work with experimentalists to try to come to concrete predictions to test arrival time theories or models, or that would be for me very exciting. And so I'm interested in working together. I'm working together with Siddhant Das on an electron beam experiment design right now. So I do notice that in the community, if I talk to people when I'm at review panels or things like that for funding, then I find that usually the response is not too positive, and that there are not many targeted calls for tabletop, not too many, for tabletop experiments along this direction. And maybe that means we got to become more concrete, and that more experimentalists should be involved with philosophical and theoretical mathematical efforts. And I would certainly be willing to promote that. My background is that I've done the electron diffraction experiment. So if you look at Wikipedia, the movie of the buildup is the one that we took in our lab. I also have femtosecond electron pulsed sources. We're working on a femtosecond electron detector right now with timing capabilities in the femtosecond domain. And that is, to me, very exciting. We hope that that's going to work soon. And so any design that can test these is wonderful. There's one thing, though, that I also want to comment on. Tim said that, just before the electron hits the detector, which in my case is a chevron channel plate. So how big is it? Well, it's funny. When I talk to theoretical people, they often don't know how big these detectors are. And I'm happy to fill in the holes. I mean, these holes are about 6 micron large. And the diffraction beams are about 100 microns apart. And if I use a lens to see the diffraction pattern, I could show you the pictures of that. Then the dots you see, for instance, the famous Tonomura movie or our movie that's on Wikipedia, there is a center dot founding algorithm. So the dot is actually quite larger on your actual screen. What you're looking at is a average position measurement of the cloud of electrons that landed on a fluorescent screen, and you calculate the center, and that's where you put your your measured dot. So actually there's more blurriness in the real experiment, at least for the electron double slit case. Now, of course, when Tim says that the electron before the double slit should be localized, and he likes pilot waves theories, I like that too. Of course, also played with we've rebuilt John Bush's oil droplet experiments. Lots of fun to play with that. That is inspirational, obviously. And then the next day, when I go to the Mach-Zehnder interferometer and I take electrons from the zero order diffraction beam, the first order diffraction beam, which are much further apart, and there's full coherence between them, then in my mind, suddenly that electron is not localized in front of my detector hole, but it's certainly somehow delocalized. And my thinking changes again, because I don't want to apply pilot wave theory to full interferometer, even if you can. Then I know that I'm rather schizophrenic in thinking about modeling of these things. Anyway, I wanted to be supportive of the stuff and state that, I'm interested in promoting this, and also promoting this to funding agencies, and maybe by reaching out and saying that there is something to be tested here. And I don't know exactly to do that, but I'm happy to band together with people if that is supportive. So those are just comments, not a real question.
That's great. I mean, let me just make a couple response comments. I mean,
Sure.
the thing you said, and again, these details about the exact experimental setup, look, I have the excuse of being a philosopher anyway. But these are all things that I just never learned, right? They weren't discussed in anything I read, because it was at this other level of abstraction. Obviously extremely important. And if nothing else, to get people who are spending a lot of time thinking hard about this to realize there's this entire other part of the enterprise of doing empirical physics that, by the way, you haven't thought of much. I think that's extremely important. The example you gave, I mean, I didn't understand. I understand. I think what you said about projecting out these points from the data that's more right spread out. And again, I think that's a perfect example. Of course, that's what anybody would do. And it's a reasonable thing to do. You should just be aware when you're doing it that you are doing it, right? That there is an additional inferential step with an assumption that's being deployed there, right? Because it's all of those steps that are somehow getting you from the theoretical description to the actual empirical data that we want to think hard about. So it's just foregrounding, right? How important that is. The other thing, and this is going to be maybe much more controversial, but I imagine you'll agree, you're sitting around funding tables. The high energy people have done a good job of convincing a large number of people that all the action's in high energy, right? I mean, and there are some advantages to high energy, especially that certain details kind of wash out, blah, blah, blah. On the other hand, the people doing really cryo stuff and Bose-Einstein condensates have also had a nice story about, oh gosh, we get it down to almost absolute zero, and the coherence effects ramp up, and we can see the quantum nature of this. So, they have a story, but this like middle scale room temperature tabletop regime, which would, I mean, just ideally be a great place to be able to make progress because it's a hell of a lot easier than either of those other two regimes. I just don't think they've had the narrative to capture people's imagination. And I think this is the narrative that could do it. That's why I'm out talking about it.
Great.
Let me make one final comment, which is when you said, well, when you go to the Mach-Zehnder interferometer, this one picture switches out in your head to another. Again, if you read, that little quote of Bell, I focus on the point where he says, is it not clear from the smallness of the scintillation we're dealing with a particle? But the second was, is it not clear from the interference bands that we're dealing with something like a wave, right? So in his case, of course, and this is the advantage of the theory, you have both elements. And they both play a physical role. And so it's not really schizophrenia. It's just, thinking, okay, in this setup, let's think about what the wave is doing, and then, so it's not that you're like really alternating. It's just different focus on the two parts of that particular ontology. So, that's why some of us find that congenial, right? It doesn't prove it's right, but it's congenial, and you sort of understand why.
Okay, great. So we have a couple of questions left. Let's head on to the next. Jiwon Jung.
Oh yeah. Hi. So if I understand you correctly, in your talk you emphasize making explicit the separation between fundamental laws, initial conditions, and the bridge principles that connect the theory to the measurements. But if I think of Newton, for example, his method of fluxions in celestial mechanics, the same mathematical machinery seems to function once as a tool, as an approximation law, and as part of the bridge to observation. Historically, it looks very hard to distinguish this rule. Would you say that your separation is meant as a normative reconstruction rather than a description of an actual scientific practice? And what, in your view, is gained philosophically by enforcing this separation instead of starting from the fact that in real practices this ingredients come as one tangled package whose limitation are acknowledged from the outset? That was my question. Sorry.
Okay, your audio was not entirely clear. I think I understood a lot of the question, so I'll try
sorry,
to answer what I understood. I'm sure I missed some of it. Look, let's take the Newton example. It's nice because Newton, thinking about Newton just gets rid of a lot of the stuff that can, create smoke and other problems. So sure, we think Newton's gravitational theory, and that's really all he laid out in Principia, was the gravitational theory. That was the only force law he had. That actually made testable predictions, right? For rates of fall, for eclipses, for, orbits and so on. Well, did it? You stop for a second and you say, well, surely, actually, just from that, you could make zero predictions about astronomical phenomena. Why? Because they're optical, because the evidence was optical. You use telescopes, right? You had to watch, you had to look, and you can read Principia from beginning to end, and you won't find an optical theory. I mean, he had a different theory in optics, but he didn't deploy that. Right? So what was going on? Well, it's clear once you say it, it's obvious that's true. And once you say it, it's obvious what the answer is. He was essentially using what we call geometrical optics, and assuming that light travels in straight lines and that, that telescopes don't distort in terrible ways the light that's, coming into one lens and the light that's going out the other lens. And you could even use your geometrical optics to give a kind of theory of the telescope and so on. But that wasn't foregrounded, right? And I think this is actual physics. When I say this is actual, I mean, I put the methodology of actual physics because you think, okay, in history, there were theories put forward and data put forward as evidence for or against those theories. And in order for the evidence to play that role, there had to be a way in which, starting with the theoretical assumptions, you manage to get to predictions about the observable data. And then once you see that, you see, but the theory offered was never enough to do that by itself, right? By itself, it just never was. It wasn't for Newton, it wasn't for Einstein, it wasn't for Maxwell, it wasn't for, for Boltzmann, for nobody. So it's just always been the case in the way physics is done that some assumptions, simplifying assumptions, had to be deployed to secure that connection between what could be described purely in the language of the theory and what could be given to you from the lab. Now, I think there's no other choice. And I think it's methodologically useful to focus on that, right? I mean, maybe in everyday life, things like, oh yeah, he's using geometrical optics. He's assuming that telescopes are reliable, right? I mean, that's all fine and good until Galileo comes up against the Catholic Church and they decide to blame his telescope for his observations, right? I mean, you know what happens when somebody decides they don't like the theory and then they decide they're going to go after some, there's a lot in philosophy of science about this, these auxiliary assumptions that are always floating around that have to be appealed to get from the pure theoretical language to the language of the data. Usually it's just done without much thought. As I said, it's done when you just show the picture of the two-slit experiment without the screen and say, hey, that explains the screen, right? That would explain from the basis of this theory why you see on the screen what you see. Then you have to say, well, wait, I mean, how did you get from one to the other? Now I'm not saying it's all that hard to fill in the gaps. It's just important to understand what the gaps are and how they're being filled in. So I don't think of this as rational reconstruction. I actually think it's the opposite, right? Rational reconstruction, as that term was used by Carnap, say, was the idea that, okay, actual physics was messy, but if people had been smarter, if people had been cleverer, if people had been more careful, they could have done it in a more rationally acceptable way. That's rational reconstruction. No, I'm interested in actual physical practice, right?
Yeah.
Here. And in appreciating, again, the gap between these idealized accounts and actual physics. So it's the opposite of rational reconstruction. It's, actual deconstruction or something. I don't know what to call it.
Thank you for answering. I was the first year in the bachelor, so I've been really nervous to ask this question, so I need to use my script to ask you. Thank you.
Sure.
Okay, thanks. So we have 3 more questions. The next question is by Lev, and in the meanwhile, I will hand over the moderation to Fabian, for I'm not sure how long I can stay. Thanks anyway, and Lev, please go on with your question.
Thank you very much, Tim, for this very inspiring and interesting talk. But for me, it was a little problem because I feel that as a physicist, I'm really thinking like Laplace and Demon. And when you putting all these complaints that it cannot be true, I put in a kind of big letters on my notes, approximate. I am approximate Laplacian demon. And then I think when you, the next hour, he was kind of trying to say that, yes, this is what I understood, but maybe I misunderstood you. I think that physicists think like approximate Laplacian demon. It wasn't exactly how you presented, but this is how I got it. And maybe one more question. Then you said that you see a spot of electron in a screen, and this leads you to Bowman continuous trajectories. But I think you will not disagree that today there is no any real evidence for difference between interpretations. There is no experimental way to say that Bowman interpretation is correct and not many words or any other. So then you say, you go to one experiment, you see something which seems to you like Bowman, and then you say it's Bowman. But careful experiment tell us that there is no way to distinguish between interpretation if you go to a real experiment. So
Good. Okay. Thank you, Lev. You're exactly the person I had in mind when I started this and said, it's easy to read Laplace or Bošković and then think that's not a purely mathematical comment. That's a kind of approximation to what's actually done. I mean, what you said when you said you think you do that, and I don't think it's anything particular about you. I think this is just a very natural thought. Anybody who reads Laplace, anybody who reads this thinks, okay, and as you say, immediately you're going to say, of course, we don't have this infinite mind, we don't have these infinite resources, we can't really do what the demon can do, but we can be kind of sub-demons, right? We can be kind of imps or something, not quite as powerful as demons, but and I guess I tried to indicate, admittedly in a little bit hand-wavy way, places where I thought this story about approximation and idealization from the pure theoretical description, that, yeah, I can see where that can take you a certain distance, right? And I tried to acknowledge places where that could happen. But the main point was when it comes to the interaction between the target system and the apparatus, I don't think that you get it that way. I don't think you can. Okay. I mean, so there is this very specific point where you say, I can even at an approximate level, as long as I'm dealing with a relatively small system with relatively few degrees of freedom, the calculations are too hard to do exactly, but okay, I can approximate them. I can use perturbation theory, blah, 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 blah. I agree. I absolutely agree. You can get a certain distance there and you'd like some epsilonics to understand, how much you're losing in the approximations, in those approximations. But the point where Einstein comes in with his thing about the clocks and I come in with the thing about the screens, I think that's just qualitatively a completely different situation. And I don't think you can understand that we handle that in anything like a Laplacian way. Now, you're not convinced by that. I understand. I have enough experience with you not to expect you would have been convinced by it. But I do want to acknowledge, I mean, you do acknowledge that's the way you were thinking, which is great for me. So you're just an example of the kind of thinking I was trying to worry about. I'm giving you the bones I'm perfectly willing to give you about where I think idealization and approximation in a certain fairly uncontroversial sense can come in. But I think to get to the formation of the spot on the screen from what you can actually calculate, yeah, I don't think that there's a Laplacian way we do that, even approximately. Now, I should say you overstated, let me just say one more thing. You overstated what I was trying to say about the pilot wave theory. I certainly wasn't saying it's proven by this or it's the only way of doing it. It's just the kind of approximation or the kind of assumption you can deploy if you have a located particle to connect that with the location and timing of the formation of the spot is quite straightforward in a certain way. And if you don't have such a localized thing, you just can't do anything like that. I mean, I don't know what you are going to do. And I think if you can't do anything, then your theory's not making any predictions. So this is, of course, where we're going to disagree. You say, oh, we all agree, they all make the same predictions, but I don't agree that many worlds makes any predictions. So here we're really as far apart as we can be, right? I don't think that you can even deploy these kinds of, straightforward approximative assumptions. I don't see how to get spots on screens out of many worlds. I just don't. It's too high dimensional. Doesn't connect to space time in the right. Now you have a very specific way of doing many worlds, which is also different than many other people have. So that's yet another discussion. You do believe in locality, and you do want some local ontology, which many worlds people don't obviously have and don't straightforwardly say. So talking about many worlds and then talking about your version of many worlds, I mean, these are even two different conversations. And I'm sure I was not attempting, anyway, I was not attempting to convince everybody that this is the only way to do things. I don't even think it is the only way to do things. It's just a way of doing things where it's particularly clear what you're doing and where you're deploying these extra assumptions and what the extra assumptions are. Okay?
May I just add one small reply? It seems that what you propose is a theory about electron, and then there are measuring device and we observe it. And I think, at least when I think about many world interpretation, and also when I look at my experiments, I think as much and maybe even more about the interaction with my measuring device. This is part of the theory. And also the interaction with my experience. In many words, the half of the theory is to explain my experience. So it's not just the ontology of my electron is not enough. I have to understand the ontology of my brain to explain my experience. This is how in many words I can make sense of the outcomes. I have to have this another half of the theory, not just theory of the electron.
Well, best of luck to you, Lev. I mean, as I say, I don't even understand experimental apparatus well enough. My neuroscience is really, really very primitive. If I had to go through neuroscience to get to the predictions, then you just wouldn't make predictions. I mean, if you say you have to go through neuroscience and solve the mind-body problem to get predictions out of your theory, okay, you can't get predictions out of your theory. Period. Because you can't do that. You just can't.
I didn't like Girardi when he replied to my attack on his theory that you have to go to the brain. So I agree that this defense is not great, but we need more time.
Okay.
All right, let's go next in the question queue. Rudi, it's your turn.
Hi, Tim. Good to see you.
Hi, Roddy.
I'm curious about how you think about a certain simple example. The example is about whether the trajectories in the presence of detectors are the same or close to what they would be in the absence of detectors. Uh, yeah, I would be inclined to say that. Okay, so it sounds very plausible to say that the detector finds the particle when and where it actually arrives, but it seems to me much more questionable whether this place and time will be the same as it would have been for the arrival at the same surface without the detector. So for showing this example, I need some kind of drawing. So I tried to draw. So I took the picture that you also had on your slides of the Bohmian trajectories for the double slit, and here I tried to draw some surface in this thing. So maybe you can see that in blue. So this surface is where I want to put the detector. So for the upper slit, it's kind of close to the slit. And for the lower slit, it's kind of far from the slit.
Away. Yeah,
and
got
then
it.
in between, I just connect the two parts. Okay.
it.
So this is a kind of surface for which I think many people would think that, okay, then the trajectories will look a lot different in the presence of detectors than in the absence. Because the kind of this part of the detector will collapse the wave function or create decoherence, so that you will no longer have this interference between the two parts of the wave function, and therefore you will no longer have these wiggles.
Right.
Okay. So that's basically I was interested to hear whether you also think of it that way. So I mean, it raises the question. Okay, if there are some surfaces for which the presence of detectors along these surfaces will cause the trajectories to be very different from what they would have been in the absence of detectors. Okay, it raises at least the question, for which surface will that be relevant, and for which surfaces will it not be relevant? So so when you discuss the double slit experiment with the idea that the detector is just along this surface, yes, I agree that the arrival times and places in the presence of detectors will be more or less the same as in the absence of detectors, a kind of far field situation. But okay, so in general, one has to be careful with this kind of assumption, and this is kind of a simple example where things could go wrong, raising the question under which conditions will this assumption be justified?
Right. And let me give, I mean, of course, I agree with everything you said. Let me give it just, again, take it out of quantum mechanics, because quantum mechanics always raises its own problems. I mean, think about just doing regular thermodynamics, and you have a heat equation or whatever, and you make predictions about temperatures of some liquids when they mix. Yeah. And you say, okay, I kind of can calculate my way to that. Now, what do I do in the lab? Well, in the lab, you then stick a thermometer into the liquid and you get a reading. And now you say, but wait, does that thermometer actually read close to the temperature of the liquid before I stuck it in? And then the answer is going to be, well, it doesn't give you exactly the same, because unless the thermometer happens to be exactly the right temperature, if anything, it's going to read, the temperature at thermal equilibrium. How close is that to the temperature before I stuck it in? Well, that depends on how big the thermometer is and how small, the sample is, and, what the coefficients are. And of course, you could imagine situations where actually sticking the thermometer in has such a huge effect that the reading you get at the end more reflects the initial temperature of the thermometer than it reflects the temperature of the thing you're using as a detector. Now, I think in that case, we would be reluctant to even call the thermometer a detector anymore. I mean, this is just a linguistic comment that often when you deploy the concept detector, there's some assumption that it's not significantly affecting the thing you're trying to detect. Of course, it's going to affect, it is, as we all agree, going to have some effect. It's a physical item. It has to go into the physical analysis. And I completely agree with you. The situations where the object has a large, effect, and those where it has a small effect are not, that itself is a theoretical question. And you have to approach it with at least some tools of theory. So yeah, I think I agree with everything you said. I mean, the picture I'm getting is not the naive one, I hope, that detectors work by magic. We know they don't work by magic. We know they work by physics. It's the question of to what extent can we really, from foundational principles, take into account the physics of that? And it's not as much as the demon could do, right? And I think that's important. Yeah.
Thank you, Tim.
Hey, Will, it's your turn. Please go ahead.
Hey, thanks. So yeah, thanks, Tim. And yeah, just to build on Roddy's point here, this question of screens, I think you mentioned Bohr talking about two different types of screens, one that does a momentum measurement, one that does a position measurement. I just want to point out that the no screen does a position measurement. And this is actually a subtle and very important point. If you think of a position measurement as this sort of instantaneous measurement that satisfies the axioms, that's just not what a screen that's just sitting there does. And so in a way, neither of Bohr's examples really connect with what happens in the lab or really with what happens in the theory. And so I think, if you think about how pilot wave theory explains anything, like you raised the double slit, Stern-Gerlach is the same sort of situation. You have this very plausible, assumption. You say particles, do this sort of splitting thing. What does that tell us about where marks will show up on a plate? There's really plausible assumptions you can make about, how those trajectories are related to the marks. But in the actual experiment, there's a passive screen that's just sitting there. And so I think, something for pilot wave theorists in particular to think about is that the effort seems to be to bootstrap position as the fundamental thing that particles have. But that's not actually how the argument works, even for Stern-Gerlach, because it's not about instantaneous position. It's about position across time, right? You're trying to say, like, where would the mark be? I know where the particle would go if the screen's not there. Where would the mark be if the screen were there? Mm-hmm. And so I just wanted to ask about this. There's a strategy which I think of as demon-like that to resolve this within all sorts of different theoretical circumstances, but it comes up a lot in pilot wave theory, which is to say, well, at the end of the day, we're going to cache things out in terms of position by using pointers at the end of the day or ink on paper at the end of the day. Like, we're going to model everything until we have something where the position is recording what we assume we did a measurement of. And so to me, like the theoretical tension, even within pilot wave theory, is understated if we don't sort of acknowledge that those sorts of like very extreme assumptions about the theory being consistent out to some endpoint where things cache out in terms of position is needed, and that has theoretical consequences, right? Like whether or not somebody's committed to POVMs will depend on whether they use this crossing logic or this end of the day logic. So I just wondered if you could say how you think that relates to...
Yeah, I mean, I think I just want to be careful that there's a kind of trivial point that's correct and then a very non-trivial way to try to leverage that point. Yes, of course, at the end of the day, in a certain reasonable sense of the end of the day, you could say the data that, because I was worried about how do we connect this theoretical physics to the actual data that we use to test it. And someone might say, well, at the end of the day, the data is ink on paper, right? Which it is. It's reported, it's printed in a journal somewhere. Now, that's true. One certainly hopes that one doesn't have to carry out the theoretical analysis all the way to the ink on paper, the way the demon could do costlessly, because we can't do that, right? We just can't. Now, I'll go back to my example of Newton, right? You say, okay, how does Newtonian gravitational theory make predictions about planetary orbits? Okay, there are idealizations. You now idealize the planets as points with certain masses. That's an idealization. You kind of can't solve above the two-body problem, but okay, you do something, you do some perturbation theory, blah, 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 blah. But of course, the data isn't the positions of those planets. The data is something reported by astronomers who are looking through telescopes. Then there's all this, tacit use of geometrical optics, blah, 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 blah. Now, what you hope is that the part from the position of the idealized point of the planet that you get by just solving for the gravitational effects, that from there all the way through the geometrical optics, through the telescope, through the printing press, to the report, that's okay. That's not going to be the issue, right? That's really reliable. All kinds of little problems could crop up, but one hopes that entire process is not going to have a substantial error on the reported position from the actual position of the planet. If you're going to have a problem there, you're just sunk, right? You're dead. So yes, of course, you do have to get there in the end. I think most of that process to the end point is done by these sorts of Einsteinian promissory notes that you don't see anything that would block an ultimate, more precise story about why this is a reliable way to get information about planetary orbits. If someone were to say, no, 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 it turns out that entire intermediate process has to be treated from the point of view of fundamental physics, or you're going to make a bad mistake, then I think you've killed your theory as a practical theory, because you just can't do it. You're telling me to apply the theory, I have to do something I can't do. And then I think the theory's dead as a practical matter.
I completely agree. I just want to point out that is a tension within pilot wave theory, right? Because a lot of, as a lot of arguments do rely on this discussion of
right. One should
pointers
be
at the end of
aware,
the day.
insofar as you think you have to push further and further into the machinery of the observation to get the predictions. You should understand how much danger to the theory as a deployable theory is going along with that. That's a gambit that's really dangerous. Because even someone might even say, yeah, but if you're right, what you've just proven is that you can't use your theory to make any predictions.
Yeah.
Yeah. Because you're not the demon.
Okay, Jan, please go ahead with your question.
So if I may, follow-up question, also commenting on what Rory said about the detector. So also what you said now about pushing further into the machinery and this asymmetry between that we say we're kind of happy with position measurements, but we want to analyze detectors, how they work with time measurements. And I would really come back that it's really the question of how good this disturbance of the detector, or how large this disturbance of the detector of your system is compared to what you want to see. But yes. It's about this relative thing. And there are some fundamental principles which tell us what disturbance we can minimally expect, right? There are these Heisenberg times disturbance relations. So we know if we learn the position that well, like in Rodi's example, if we have a detector which knows, am I here or here, or and so on, then we have this minimal amount of decoherence. It will disturb our wave function, and this will affect our trajectories. We can predict this with the Bowman dynamics then. But then any real detector will have a lot more than that. So this is like the minimal thing the ideal detector could do, and then any detector we build will be much worse than this, or a little bit worse, depends on it. But the worst thing is it will annihilate the particle even completely. So it will totally change the system, not just the trajectory. And now it's just that somehow in position, we already pushed that far. So our position detectors, we have this very dislocated wave function, and our position detectors already have a very fine resolution, and the back action doesn't affect the result. So we can make this idealization. We don't need to go into the details of the detector. We don't care about this because it is sufficiently well for the interesting features of the wave function. It's fine. We know that the back action will be so small that we don't care about this. But now for the temporal features, we're not there yet. So and therefore or at least it's a way more bigger challenge. I mean, I'm sure we're there in many aspects, but at least it's a bigger challenge, and therefore there is this asymmetry, and I see this pushing into the detector models for the time resolution really as this point. It's not that that somehow one does no longer allow to make this idealization, but the idealization is warranted in the position case, but not warranted in the time case if you really want the time resolution.
I understand what you're saying, and again, the details of the mechanisms of clocks used in these circumstances, I don't know well enough to comment. I do want to make a slight comment about the Heisenberg uncertainty relations, and I mean there was part of what you were saying which I think addresses a completely different issue, which is what's normally called the post-measurement state, right? So by the normal, and this had to do with the idea of non-destructive measurements and so on. So by the normal Heisenberg kind of reasoning, if I could manage to do a position measurement with extreme accuracy and then project onto the eigenstate, I mean, with perfect accuracy, okay, there's not really a state there. It's a delta function, but whatever. Okay, I mean, make it very, very small tolerances. That just because of the way quantum mechanics works, that state itself would be of a very high uncertainty and momentum, right? I mean, that's why I can't create any state where I can simultaneously predict both the momentum and the position outcomes beyond the Heisenberg limits. But the question of the post-measurement state, it seems, is not relevant to any of these experiments. I mean, nobody's doing post-measurements. The particle just hits the screen and it gets absorbed. I mean, it disappears. Nobody cares what its state is post-measurement. It's not coming into the analysis. So the real issue is how much does the presence of the screen influence the particle and make it different from what it would have been, especially just before the interaction, what it would have been without the screen, right? There's this counterfactual comparison to where it would have been, which maybe we can even cleanly calculate, and where it actually is, given that the screen is there doing something. And as Roddy said, and we all agree, you can imagine screens, or I don't know whether you want to call them screens. You can certainly imagine physical devices or physical things that you stick in there that are going to have a hell of an influence on that particle, right? So, the real question is how strong and of what sort is that influence? How good a guide is the clean calculation I can do without it there to what the calculation I can't actually do but wish I could do with it there, right? The calculation that the demon could do with it there that I can't do. And as Roddy says, I hope we all agree that there are devices or objects or whatever whose influence would be massive. We hope there are devices whose influence is not so massive, or if it's large, it can be accounted for, right? Even if it's a large influence, you could somehow, work out from what you see what it would have been without it. I mean, something like that. And it's just that we need to think about the exact logic and the assumptions that are going into those steps. That's all.
Okay, so yeah. I don't want to get us off track, but just quickly regarding this post-measurement state. So as I imagine, at least it can also be a continuous process. You have some interaction which is part of the measurement, and then you have a post-measurement state. You could say after this interaction. So it's a continuous modification of the state, and then depending on what you learn during this, I don't know, time interval, you disturb some a little bit. So
I mean, look, you could do what are called weak measurements. They're just another physical interaction. They happen not to have at all the features of these idealized von Neumann measurements, right?
Sure.
And importantly, don't. But there's some kind of physical interaction between your system and some device, and you hope that your theory could help you make predictions about what state the device will end up in. if you do that. And then you need to, of course, account for the device, as you say. If the point of weak measurements is to make the back reaction very small, but then make many measurements and, blah, blah, blah. All that's perfectly reasonable, of course. I mean, whatever a measurement is, it's a physical interaction. And we all agree that the theory ought to, in principle, be able to handle that, even if in practice we can't use the theory in a demon-like way to do that calculation. That's my, yeah.
Hey, please go ahead.
Okay, so I want to challenge the community, which is this. I really appreciated Roderick Molka's question. Close one slit and then see what the arrival time distribution is. I can do that. Within a nanosecond, I think it will take me a year to do it. Within 100 femtoseconds, it's very challenging, but I think I could do it within 3 to 5 years. And I love it. So the challenge is, though, if I need to propose something to get some money and people to do it, then we need concrete calculation that say, now this slit is closed, and this is the arrival time distribution, and you need to measure it down to this timing to make a difference between, model one, say a standard interpretation with some, imaginary potential absorbing detector model versus, let's say, a de Broglie-Bohm arrival time distribution. And if you can get two of these models that give a different distribution, different answer, then man, I'm super excited to try to go after this. Now, another comment is on what Lev Weitman said. He said, right, I have had the pleasure to have a nice walk with Lev in Italy. So one of the smartest people I know. But the deal is, I disagree with Lev. He said that that Bohmian mechanics is just an interpretation. Well, maybe this arrival time problem, and given that the literature that some of the people here have fed me show that different detector models at the end give different temporal arrival time distributions. That's what this community is telling me. And I say, okay, then it's testable, and maybe there are differences. So I want to know, is Lev just right or wrong? If it's simply an interpretation, then there's nothing testable there. And I don't want to sorry, I'm not going to say waste. I do not want to spend time there. Time is the most precious thing I have. And the deal is, if Lev is wrong, then you got to slam it in the face and say, here's the evidence where Lev is wrong. I mean, I think his question is completely and utterly pivotal. And for instance, the suggestion that Roderick Tomolka had is a specific example of something that can be calculated. Right? You might also think of dynamical closing. If I think of, say the guiding wave is not the Schrödinger wave, but like people in stochastic electrodynamics would have it, it's an E&M wave that travels at a different speed than the electron wave, then dynamical closing would, whatever. I mean, depending on how further you go out there in models, you might even have a motivation to expect differences. But the deal is, we need concrete stuff that says, this is where the numbers are. Otherwise, I can't even go to a funding agency and say, hey, guys, give me money for a postdoc grad student, and I'm going to dump my time in there and build something because they're going to laugh me under the table. That's my reality. Okay, that was my end of my comment.
Lev, please go ahead.
So may I just clarify? I absolutely agree that depending of what kind of screen or what kind of detector you put, you will get different results. In fact, I think that this is more a problem, because if you have it in a detector which can tell you with infinite precision the time of arrival, whatever it means, this detector will not find any particles due to Zener effect. This is why I think the time of arrival is really problematic concept. So, I'm sorry, Herman, I'm not sure that, as far as I know, there is no any experiment which you can perform to distinguish between Bowman approach or many word interpretation, at least. So then it's not, I'm not sure that the experiment here, I think what's very interesting is what I know that Jan is trying to do, what Ephraim Steinberg was, I think, did, but not very good. It's to show the surrealistic trajectories which were not mentioned. They're interesting. It's not clear if it's plus or minus a Bohm interpretation, but there are this interesting situation when the behavior of Bohm trajectory is very different. Again, you cannot see them, but at least you can make the situation in which you will get them. And this is, I think, interesting experiment.
So let me make a comment here because, Gleb just stepped on a landmine that Will had already, mentioned this. And if anybody doesn't know, if one tries to model for the sake of understanding how to make arrival time predictions, if one tries to model the screen as making a very rapid and in the limit, infinitely rapid succession of position measurements at different times, waiting to get a result, right? Waiting for something to show up, then for sure you're going to get the quantum Zeno effect. And that kind of detector would have a massive influence on the wave function of the particle, so massive that, as he says, the particle would never show up. What does that prove? It proves that's a damn wrong way to think about actual screens, because actual particles do show up on actual screens, right? They really do. So that just shows that this model is absolutely the wrong model. And Will's point forever has been that actual screens are not active in that way. They're passive. They're not making these infinitely fast chops or whatever. Yeah, that would be really, really, really interfering. But that's just not what they do. So if that's the best you can do to model how time data comes out of labs, that's as the worst disaster you can imagine for such a model, because it tells me no data should come out at all.
But they also will not tell you when exactly the particle arrived. It's not the real screen, doesn't tell you when it's arrived, it only to tell you where it is arrived. And this is much less problematic. You can measure position. The time, you need this, what you mentioned, and then you have Zeno effect. This is exactly the problem.
You don't need that. I mean, just ask Herman. That's not what he does.
I don't
He
know.
has clouds.
No.
Okay, so let me interject. So let's make it concrete. I'm not saying I'm making a statement on who's right or wrong. I have no idea. However, suppose I make a screen, right? And the screen I excite it with a femtosecond laser pulse so that when the electron arrives, a secondary emission will only take place when the screen is excited. And I excite that with my 10 femtosecond laser pulse. So I make a 10 femtosecond electron source. Here it comes from the left, it flies. Here's my screen. It's a flat surface, atomically flat. I hit it with a 10 femtosecond pulse, goes into excited state semiconductor, electron hits it, makes secondary. And now only when the laser pulse and the electron are there, I detect it. It's kind of like a streaking thing or whatever, but now defined in a surface. Okay, that's the type of detector I would have in mind for fast detector. Now, if you take, for example, such a detector, where does this discussion go? I have no idea, but I'll leave that up to you.
So, again, you have to analyze how it's changed the probability of detection. I'm sure that the time is very small. It will change very much the probability of detection. Maybe it's also be dark count, which is also not good.
Yeah, sure. There's details, but the deal is, okay, what is wrong with what I said? If different people,
no, but there is a theory.
Models,
no detector will find you precise time of arrival,
of course,
and find particles. This is Zeno effect is a real quantum phenomena. You cannot avoid it.
Of course.
I mean, look, it seems to me, Lev, this is kind of point. I mean, you could say the same thing about position.
No.
If you could give an exact position, then you'd have to go to a delta function, and then the energy would be infinite, and then the entire universe would blow up. So you say, well, gee, you can't have perfectly precise position measurements. So what? I mean, that's just not relevant to any actual issue here, right? We're talking about things you can do and data you can collect and that you want to account for. So if you say in some absolutely idealized case nothing will work, okay, all that proves is we're not using absolutely idealized cases. How does that help us?
But conceptually, only as an energy.
Conceptually about what? I want conceptually about actual experiments. I don't want conceptually about idealized experiments that won't work.
Okay, maybe we are talking about the regime when Zeno effect is not relevant. Maybe so then it's okay, but still it's okay. But the details of how you do the experiment. This is what's very important.
It is.
So then, as you mentioned, that your screen might change the result. So you have to look very carefully. If you put screen, you put your detector, fast detector, you put the pulse, laser pulse on detector. It's all might influence, and it's all. But in the end of the day, I believe it all will show quantum mechanics is correct up to infinite number of decimals. This is what, at least until I die, I will be very surprised that somebody will find that quantum mechanics breaks down. So, and now, but Bohmian mechanics is not quantum mechanics breakdown. It's not. It's the same prediction. So I don't think that I should be afraid of this kind of thing.
Right. I mean, I don't agree with that, and a lot of other people don't agree with that. I mean, we don't want to get into that argument here, but for the record, it is not universally or even widely accepted that those theories make the same predictions.
But about Bohmian mechanics? Yeah. So that you are welcome. I just this contribution to the book of Detlef Dürr. I think I made the analysis. Please find what's wrong with this analysis.
Okay. We'll have a discussion sometime.
Yeah, okay.
Okay. I think Aurelian's hand is up. Please go ahead.
Oh, yeah. Thank you. So I wanted just to say that's one of the most interesting talk you got. I think I like very much this discussion about the Laplace demon. This is very, very central point about realism. And but I have also instead of discussing about Einstein and these kind of things, I would directly go to the problem about seed and dust and a project, which is very, very nice. And I'm very supportive as well, like many people here. But my point is we have to be very careful about one element is that nobody has ever seen an electron. What we watch is always a macroscopic pointer in the end of the day. So we have to be connected with some kind of instrumentalism and positivism in the end. And of course, this is very clear, but the Bohmian mechanic until now rely very strongly on POVM. And I think we have to be very careful and prudent and to see if we can define in the end POVM are adapted to this kind of measurement. And I really hope that is the case. But if we do that, it could be that maybe the measurement will not be so directly understood. Maybe we'll have to be very prudent in and in the end, if you want to watch a current which is leading to backflow of a process like that, which is exactly the prediction of the Detlef and incident calculation, it could be that the measurement will not be the intuitive kind of approach that you have in reality. It's just put a detector and watch the result. Maybe we have to make a lot of post analysis after this. And if it is so, then it will not mean that Bohmian mechanics is false, but just that our prejudice about classical physics are wrong.
Yeah. Can I just say, I completely, I mean, one thing that I find discouraging is if you think about it this way and you say, look, I admit that to make these predictions, I'm putting in certain assumptions, and I admit from the beginning they're assumptions, and I certainly admit they're only approximately true, right? I mean, nobody thinks the screen doesn't have any effect. The issue is the magnitude, right? And the type, and depending on the screen and depending on the situation, how strong is the effect and so on. we all agree that, yes, we would all love to be demons who could figure all this stuff out from fundamental principles. It's just that we're not. Okay. The thing that discourages me is that exactly because if under reasonable looking assumptions, you can get predictions that can be actually tested in the lab, the kind of thing that Herman, given enough time and money, could do. And even if under different kind of plausible looking assumptions, those predictions came out differently, then man, we ought to be doing this, right? Because that would be pointing us to where we're deploying some assumptions that turn out not to be correct, or where the more analysis has to be done, or where there are effects we weren't expecting, and so on. But that feedback has to come from the world. And, you know, what I would be happiest about is that even people who have very different beliefs about how all this should be carried out or could be carried out could agree that let's do as much analysis from every point of view you can think of. Do as much analysis as you can, deploy whatever assumptions you think are reasonable to where you can get predictions that could actually be discriminated in the lab, and then go and lobby people to fund it. Because that's actual progress, right? I mean, yeah, somebody's going to turn out to be wrong. Okay. I mean, I'm not, you know, I may have opinions about how I think it'll come out. I'm not wedded to those. And if the experiments come out contrary to my expectations, I've learned something good. You know, I'm not like scared of that. And nothing can happen to rule out. And there's this other thing that I find very strange. I don't think any results could, as it were, rule out the basic pilot wave picture as a framework to try to develop, right? Taking account of whatever you found out experimentally. I mean, maybe there are other frameworks that can be deployed that'll do better. Good for them. I don't have a problem with that either. But it just seems like, you know, we've gone for half a century with string theory all being done at this high level of abstraction with zero empirical input. And here we seem to have a way forward to get into the lab at a moderate cost and actually get some results that would be relevant to understanding which of these approximations seem more promising than others, or which approaches seem to be able to actually come up with the right numbers. And I just hope that the underlying disagreements don't block the importance of that project, because to me, it's an extremely exciting project. That's all.
All right. It seems like we're coming to an end of the discussion. I don't see any more hands left. All right. So I guess it's time to thank Sting for such an engaging discussion session. And I would just make a quick announcement for our next talk. So we will start again in the next year on January 12th with Catalina Cusiano. And we will have a quite busy start of the year with many talks. So be sure to stay tuned. And I hope to see many of you in the coming year. Thanks again. Bye.
Ciao.